Everest is the highest peak on Earth, rising to 29,029 feet. That's 8,848 meters above sea level. And according to observations, the mountain is still growing, increasing by about 0.16 inches or 4 millimeters per year. But what if one day it catches up with the Martian Olympus Mons, whose absolute height is 69,649 feet, that's 21,229 meters, and breaks the elevation record for our solar system? Then the summit of Everest would be available not to elite climbers, but only to astronauts. If Everest continues to grow at the same speed as it is now, it will catch up with Olympus Mons in 4 million years. Can a mountain grow for so long, or does this growth have limits? Despite its permanent appearance, the surface of our planet is very mobile. It's constantly changing, invisible to the eye, thanks to the movement of lithospheric plates into which the Earth's crust is divided, 7 main plates and 152 smaller fragments. This mechanism also leads to the formation of mountains. When 2 plates collide, the impact force causes the rocks at the point of contact to compress, thicken, and move upward like a carpet pressed against a wall. For example, the Himalayas in Asia, with its 10 peaks, the 8,000ers, including Everest, appeared due to the meeting of the Indian and Eurasian plates. This process has not yet finished. The Indian plate continues to move at a speed of approximately 7 centimeters or 2.8 inches per year. So the Himalayas are also constantly growing. Of course, the collision of tectonic plates does not always result in the birth of such giants. For example, Mount Witchyproof in Australia rises only 486 feet. That's about 148 meters above sea level, for which some call it the smallest mountain on the planet, while others consider it to be a hill, since it doesn't meet the generally accepted definition of a mountain. But the formation of these landforms is not only caused by tectonic forces. There's another geological phenomenon that leads to the birth of mountains: volcanoes. This happens due to the rise of the hot mantle stream from deep inside the Earth, a plume that breaks through the Earth's crust and erupts to the surface. Each subsequent eruption piles up more lava, ash, and terrestrial rocks, which accumulate and thereby feed the mountain. The most common example, according to San Diego State University, are slag cones. They have a symmetrical, conical shape, which we usually imagine when we think of a volcano. It is these mountains that grow the fastest. They can form in a few months or years, but their average height is only about 300 feet or 91 meters, and the maximum does not exceed 1,200 feet or 366 meters. Unlike fast-growing small volcanoes, stratovolcanoes and shield volcanoes grow more slowly. The most spectacular shows are stratovolcanoes. They rise an average of 8,000 feet or 2.5 kilometers and can erupt with great force. A vivid illustration: Vesuvius, having wiped 3 cities from the face of the Earth in a day, including the notorious Pompeii and several villages. Huge, gentle shield volcanoes are less dramatic. Their eruptions are more reminiscent of the fluid flowing along the edges of the container than the soda exploding from the bottle that you shook and opened, as in the case of stratovolcanoes. Shield volcanoes grow, slowly flowing with lava, thin layers of which are layered on top of one another. Their wide base is several miles in diameter, and their steep slopes are crowned by a relatively flat peak. But why don't mountains grow to infinity? For one reason, due to the collision of the plates. For another, due to the slow and incremental growth due to eruptions. If this weren't so, then pilots would have to maneuver between them as if in a stone maze. Is it possible? No, scientists say. The fact is that along with the formation of mountains, there are also the great levelers, reasons that limit their height. Otherwise, for example, the Ural Mountains, which are more than 10 times older than the Himalayas, should be much taller and not 4.5 times lower than the Himalayas. One such reason is gravity. The sheer mass of mountains makes the Earth's crust bend and fall below them. When the weight of very high mountains is too much for the tectonic forces pushing them up, growth stops. Moreover, the collision of lithospheric plates continues, which leads to compression and thickening of rocks under lower peaks, and the growth of slopes on both sides of the highest points. So a plateau is formed. That is, after a certain critical value, the growth of mountains continues, only, relatively speaking, no longer up, but in width. According to geologists, Everest is close to this value, or may even have reached it, since the rise of the adjacent areas has begun. It's possible that its height is the maximum possible for these landforms, although scientists have not yet determined the exact threshold figure. But not only gravity prevents the mountains from growing, their height is also eaten away by ice. According to the observations of researchers, as soon as the peak reaches a certain height, glaciers appear on it, eroding the top, although this applies only to warmer climates, since in colder climates, it's the other way around. It's noted that mountains all over the world rise above the local snowline by no more than 0.93 miles, or about 1.5 kilometers. Therefore, according to this theory, the rate of glacial erosion is higher than the growth rate of the mountains. However, the growth rate of volcanoes, scientists say, can overtake glacial erosion, but their height can be affected by the loss of a source of magma. If the tectonic plate moves, the direct supply of magma is disturbed, and with it, the number of eruptions is reduced. Such a problem does not arise, for example, on Mars, where the crust does not move. Their own eruptions are dangerous for the size of volcanoes. For example, after the eruption of the stratovolcano Mount St. Helens in Washington state in 1980, winds carried 520 million tons of ash east across the United States during the day, which caused complete darkness in the city of Spokane, just 250 miles or 402 kilometers away from the scene, and the height of the mountain decreased by as much as 1,312 feet or 400 meters. One can imagine how the face of the planet has changed and how many record breakers it has lost since 252 million years ago, when, according to one theory, volcanic eruptions led to the largest disaster in the history of the Earth, which, over about 60,000 years, plus or minus 48,000, destroyed more than 96% of marine species and 70% of land inhabitants, and pushed the Earth from the Permian to the Triassic period. But these are not the only undermining factors. Rivers also influence mountains. First, they add visual height as water crashes into the edges of the mountains and erodes the rocks, creating deep crevices at the base. In fact, all these beautiful, dramatic peaks are slightly lower than the plateau itself, explains Nadine McQuarrie, a professor in the Department of Geology and Environmental Science at the University of Pittsburgh. But as rivers erode the rocks, their channels can become too steep. This, in turn, provokes landslides that carry away the material that makes up the mountain, thereby limiting its growth. It's assumed that after the river reaches threshold steepness, its influence on mountain growth is limited. Underwater mountains are also affected by gravity and landslides, but they can become taller than land mountains as water supports their sides, allowing them to grow taller. So, while Everest is trying to break through gravity and the thickness of ice, there are already champions on Earth who have surpassed it in height. These are the Hawaiian volcanoes Mauna Kea and Mauna Loa, bending the Earth's crust at 19,685 feet or 6,000 meters. So, why don't we hear stories about their conquest? The concept of relativity is to blame. In fact, Mauna Kea, whose height from base to top is 10,210 meters or 33,500 feet, and Mauna Loa with its 10,168 meters or 33,360 feet, can accommodate the Caspian Sea and the largest freshwater lake in Europe, Ladoga. They undoubtedly are the most grandiose mountain formations of our planet. But most of this splendor is hidden underwater, and according to the generally accepted definition, the absolute height of a mountain is measured from sea level. So, because of this standard, our unrecognized heroes lose a lot because their heights above sea level barely exceed 4,000 meters or 13,123 feet. By the way, Mauna Loa's prospects would probably be better if it hadn't lost a source of magma due to a shift in the lithospheric plate. So we have to admit that on Earth, climbers, even 4 million years from now, will not have the opportunity to climb to a height significantly exceeding Everest's. The laws of geophysics set strict growth limits for mountains, and Everest seems to have reached its ceiling. So the dreams of a new Olympus Mons are destined to remain dreams. Or do you know another way to surpass the giants that have already conquered the roof of the world? If you like the video, give it a thumbs up, subscribe to the channel, click on the bell to enable notifications of new videos, and don't forget to recommend us to your friends.